mentioned in my email, I graded all the midterms already. And so your grade in my math lab is the complete updated grade, workbook, pages and all. So that's the grade I went off of when I put your midterm grades into LeoNet. So, so yeah, just keep that in mind. So moving forward, all the stuff that you saw leading up to the midterm, pretty much from here on out, you will not see any of that previous material anymore. So the way this class works is after the midterm, we are on completely new materials. It's completely separate from the old stuff. So if you didn't like the old stuff, then this might be a good way to pretty much reset in this class. And so what we're going to start talking about are topics in just linear equations, so just standard high school algebra stuff. And we'll talk about statistics as well. So for any of you who are taking statistics next semester, we're going to be looking at quite a few ideas that will come up. I'm teaching statistics this semester currently, and I find myself mentioning, if you took Math 105, this should seem familiar. I find myself saying that a lot. So this would give you a good idea. And yeah, if you are taking stats next semester, I do have 2 sections of it being offered currently. But so these ideas that you learn in this class will be helpful for if you take stats next semester. And so just keep in mind the 2 due dates coming up currently. The first homework after the midterm is proportional reasoning and solving linear equations. That's due currently on the 17th. So that's on Wednesday. And the 18th is just a quiz for exactly that. Now, you might find this section pretty straightforward. Proportions and linear equations, it's just a lot of very basic algebra. And so you might be able to find yourself knocking it out fairly quickly. So don't forget about the due date, though. Does anyone have any questions for me before we get started with the new material? Yeah, I'll mention the workbook pages here momentarily. Any other questions before I move on? Yeah. Okay. Well, let's go ahead and move on to the new material. So this new unit, it can be best summed up as linear equations and statistics. So the first section will be linear equations. The remaining 3 sections will be all on statistics. And I guess I'll go ahead and start off by writing out the workbook assignment for this section. So I believe page 15, number 3 and 4, and page 16, numbers 2 and 3. So these 2, along with the homework for the next or the workbook for the next section, that'll be due Friday. If you are curious what the next section is going to be. So the page 17, that's for the next section. But if you were curious what workbook number 5 will entail, it will entail those 6 problems. Page 15, page 16, and then page 17 that I wrote at the top. That will encapsulate the 5th workbook assignment that will be due this Friday. So let's go ahead and move on to the lecture material. So we'll start off with this idea called a ratio, which some of you might be familiar with either directly or indirectly. A ratio is a quotient, or it's a fraction between 2 quantities. That's pretty much it. So you can read a ratio. So since a ratio is in fact a fraction or quotient, you can read it as A to B, comparing one number to another number. That's pretty much ratios. And so example one, we use ratios all the time when dealing with speed of, say, a vehicle. Miles per hour. Miles to hour would be the ratio in that situation. We use these quite a lot more than we understand. A half a cup of sugar, we use this for quantities when measuring, maybe for ingredients and for proportions later on that we'll see. But it's a way of comparing two quantities together or associating them in a certain way. So here we have a car that travels 10 miles in 8 minutes. Find the rate or speed in miles per minute. And so the ratio would just be the fraction that compares these two quantities. So we have 10 miles over 8 minutes. So that would be a ratio, as simple as that. But they want miles per minute. And so that means we simply need to simplify this fraction or see how we can narrow this down into some amount of miles per 1 minute. But basically, all this is saying is we can simplify the fraction. So we can back up a little bit. Of course, 10 over 8 is, it's 5 over 4, which we can simplify as 1.25. And let me go ahead and pull up the calculator while I'm thinking about it. So 10 over 8, 1.25. So we use ratios all the time. We can use them in either direction. Either if we know the rate, we can figure out the amount of, say, distance we go in a certain amount of time, or vice versa. If we know the distance we've traveled in a certain amount of time, we can figure out the rate from that. And this simple formula is ultimately, I mean, there's a bit more complicated mathematics, of course, but it ultimately comes down to this idea for how cars determine the speed you're going at when you press your foot on the gas pedal. It will determine these distances and determine a rate. So hopefully that's pretty straightforward so far. So let's go down to something that might be a little bit more complex, maybe. The return on investment. Well, what is that? Well, they tell you what it is. It's a ratio of either profit or loss relative to the amount of money invested. So they're saying the ratio of profit or loss relative to the amount of money invested. Well, they tell us that the investment is $2,800 and that the profit is $1,400. So what's the ratio going to be? So you said 2,800 over 1,400? And this is wrong. And why is this wrong? It said, so this is where the ratio, well, for the ratio, the order in which they ask for what goes first and what goes second matters. So notice they want the profit or loss first. They stated the numbers on, they switched the order of the numbers to mislead you. So notice the profit of 1,400 tells you that the 1,400 goes on top. And then the relative to the amount of money invested, well, you're investing 2,800. So I had quite a few questions about this one last semester, and I wanted to bring it up just so there's no confusion. But that's why it's in this order. It's because the ratio makes you put the profit first, and then makes you put the money invested. Well, once you figure out that ordering, that's the ratio of profit to money invested. And so, of course, that's just 1/2. It's just 1/2. So besides for that little trick, hopefully that seems still pretty straightforward. But we're not really concerned so much with ratios as we are proportions. Proportions are a lot more important, because now this gives us an ability to scale certain ratios to either larger values or smaller values. Again, this idea of proportionality is used a lot in recipes. If some recipe calls for 2 servings, but you want to make 4 servings, well, guess what you do to every measurement in your recipe? You multiply it by 2. Instead of 1/2 cup of something, well, you do a whole cup of something. You multiply every single measurement by 2. So proportions is kind of the idea behind that. And so all it is simply is whenever you set 2 ratios equal to each other. Very simple idea. And for a lot of these, well, because it is the equality of 2 ratios, which ratios are fractions, and we use cross multiplication a lot. You might remember that from high school. The cross tells you which numbers go together, and multiplication tells you how they go together. And so you can see that translation over on the right-hand side. And you might all be familiar with this, but we use cross multiplication quite a bit whenever you have 2 fractions equal to each other. So let's go ahead and apply this. We start off with example 3, solve for the variable in each proportion. So you can see in problem 1, there's a t right there. So we want to get the t by itself. Of course, my philosophy when I teach college algebra, just in general, is fractions are bad. Let's get rid of them. One way to get rid of them, we use a cross multiplication. So we can cross multiply here. 10 times 49 is equal to 14 times this variable t. Well, at least 10 times 49, we can do that fairly quickly. It's 490. And hopefully, by this point, you remember your algebra. The variable here is t. You want to get t by itself. So hopefully you remember what to do in a situation like this.
Divide 14.
Yeah, divide 14. It's going back to high school. 14's cancel. So t is equal to, well, whatever that quotient is, 490 divided by 35. Simple as that. And you'll find this pretty easy for the next string of problems when you get to this part of the homework. But problem 2 is probably the trickiest one out of that, and I did want to isolate it and have us look at it. With problem 2, the issue is there's a fraction within a fraction. It's called a complex fraction. Those aren't very fun to deal with. So the question is, how do we go about this problem? Do we change anything about it? Say no, we still cross multiply. It's just the things that we are multiplying together. So let's be careful about this. 7 times 7 is equal to m times 1/2. It just so happens that the thing that m is multiplying to is a fraction of its own. So that's the first step. That's the cross multiplication. It didn't clear out all the fractions, but it made it, well, a lot nicer to work with. And so Now how do we get the fraction, or not the fraction, the variable? Now how do we get the variable by itself? Yeah, we multiply by 2. All right, so if this stuff's very intuitive to you, you might be able to get this homework knocked out very quickly. So if that makes you feel better. You multiply 2 on both sides, and I guess I should have multiplied 7 times 7, which is of course 49. We'll just put it all together in the next step. But you multiply 2 to cancel out the 2 in the denominator, also known as a least common denominator. Well, 7 times 7 is 49, times 2 is, what is that, 98? And really all we have is technically m times 1, but the times 1 is kind of boring. It doesn't do anything. Just down. So, yes? What's that? 2 times 7 times 7. And if I make a little remedial mistake, I do it every now and again, just let me know. Does that seem good? Straightforward? Okay, well, let's unfortunately go into the word problem aspect of this section. So proportions are fine, but now we have to deal with this idea of setting up the proportion. Once we set up the proportion, then it's going to be a matter of cross multiplication. So example 4, there's a bottle of liquid cleaner that contains 80 fluid ounces, okay? One load requires 5 ounces. How many washes can be done with the 1 bottle of the cleaner? Okay, so they're throwing a few numbers around at us, and we need to get a proportion out of this. So an equality between 2 fractions. So equality between 2 fractions. So does anyone happen to see what any one of these fractions can look like?
Would do 1 lay or 5 ounces for 1 lay.
So what you said is fine. I do want to preface that with the ratios, sometimes, especially with my math lab being as picky as it is, sometimes the ordering matters. But with proportions, you could put a certain quantity on top and a certain quantity on the bottom. So I'm going to write it in 2 ways that are equally correct. You could write 1 wash load and 5 ounces. I'm just going to put OZ for ounces. Or you could have wrote 5 ounces per 1 wash. The only thing you have to do to make sure that this is okay is on the other side, the other ratio also has to have number of washes in the numerator and number of ounces in the denominator, or ounces on top, washes on the bottom. The units have to be on the same part of the fraction. So if washes are in the numerator for one, wash has to be in the numerator for the other. If you mix and match, you're going to mix up the values. So really, I'm going to go with the left-hand fraction just because I see 1 wash for 5 ounces. I'm reading it in that order, but again, it doesn't matter your order as long as your units are aligned, ultimately. As long as your units are aligned, that'll be perfectly fine. So what's the other fraction going to look like? Yes?
X washes over 80 ounces.
So we want to figure out, it even says how many washes. So X washes. And then they tell us with 80 ounces. 80 ounces. And again, if you were doing it the way that's on the right, you would write X wash over 1, that's underneath 80 ounces. So just like that. So I'm going to proceed with the way on the left. Because now that we have the proportion, we get to cross multiply. It's as simple as that. So now it's 1 times 80. Again, this might be an excessive number of steps. 1 times 80 is equal to 5 times x. We can just clean that up ever so slightly. And simply divide both sides by 5 to get x by itself. Divide by 5, divide by 5. X is equal to 80 divided by 5. Is 16.
Would I end up running into problems down the line if I decided to just read the problem to 80 divided by 5? Like, would I run into problems if it got more complicated, or?
Well, it works out this way because the numerator was 1.
Right.
So that's why
Oh, okay.
it worked out that conveniently because, yeah, when you have a quantity
If
of
it's like
1.
3 or something like that, it would be a little different.
Yeah, if that was a 3 or if that was actually literally any other number, you'd have to include that as well.
Fair point.
Yep. So 16. There will be, or in other words, there will be 16 washes for a bottle of liquid cleaner that contains 80 fluid ounces.
Yeah.
Well, does anyone have any questions before we look at another one? Not. Let's go ahead and move on to example 5. Now, honestly, in the real world, I think this would be a horrible way to determine the number of deer in a game preserve, as this problem suggests. To determine the number of deer in a game preserve, they catch 127 deer, tag them, and release them. Okay, so they tag 127 different deer and release them. Then they catch 113 deer and see that 69 of them are tagged. Estimate how many there are in the game preserve. So we see that there's a bunch of numbers here that we can go ahead and put together in some manner. So does anyone happen to see any fraction that we can form from this?
69 tag, maybe it's like maybe the second one. Then you could do 69 tag deer over 113 deer caught, maybe.
Yeah, that'd be fine. Again, I'm going to read it as 113 and 69, but again, your way would be perfectly fine as long as your units are aligned. So we can actually write that on the left side. So in particular, what these units are, now it's not really, I guess to distinguish them, of course, the denominator's tagged, just to give it some sort of label. 113, I'll just say here. Okay, cool. So that's one of them. And of course, we see the 127, so that's going to go somewhere. Yeah, that's going to be tagged because it does say 127 deer, which, okay, deer, but tags them. Okay, they're tagged. 127 tagged. So by process of elimination, there's X deer. And from here, cross multiply and all of that stuff. 113 times 127 is equal to 69 times X. I can go ahead and clean this up a little bit. And 13 times 127, it's a fairly larger number. And then we just divide both sides by 69. We're done. X is equal to whatever this quotient comes out to be, which is, they do give us a decimal, but I'm guessing this is going to ask you to round because,
You can't have that.
what's that?
You can't have like 0.9 here.
Yeah, you can't really have 0.98 here. So we're gonna take that number and bump it up to 208. Just
Why
round
would
it.
you bump it up to 208?
What's that?
Because the last year would be a full year, like, why would you bump it up to 208? Why would you round it back down to 207 since the
Well, knowing my math lab, I wouldn't be surprised if they said add 5 to it and then
right?
multiply it by pi. I don't even know, but I'm assuming they're going to ask to round up. But yeah, but this is ultimately, I guess, to try to make some real world sense of this problem. I suppose it is an estimate.
Right.
So really in the real world, they'll say 207, 208 about.
Okay.
But in my math lab sense, since everything has to be very quantified.
It'll tell you to round up for all the homework ones and you take the quiz and it tells you to round down.
Yeah, that's why on the midterm, there was that one question where it was determine the number of months or the number of periods, like payment periods, and some of them said round up to the nearest integer and some people didn't. And I thought that's, even though, I don't know, the rounding would tell you to round down, but the problem told you to round up. And so I just gave you your full points back because I thought that's ridiculous. So, some of those things are a little just, I understand why, but also I've been in school for a long time. I think that's unfair to ask. It's misleading, but regardless, we have 208. Does anyone have any questions before we look at maybe a little bit trickier one? Okay. Let's look at example 6. So I wanted to throw in a problem that might be a little bit more relevance. So Southeastern has a bunch of published surveys on their website. I use them a lot for my statistics class. They're pretty interesting. And they also have the most exciting thing to look at are retention rates, which is basically after a certain number of years, how many students stick around? Do they? Do they not? And so this would be maybe if Southeastern's parking committee was thinking about, do we have enough parking spaces for everybody? And trying to see, all right, if we admit a certain number of people, how many do we predict are going to stay around? What resources and amenities do we have to prepare for in addition to the current student body? So you can go on there, and I believe this is the most recent, 2019 cohort. So it may not be your cohort if you're a freshman. So it was about 68 out of 100 students are expected to stick around after 1 year. So the other 32, they try out college for a year, don't like it, they do something else. Maybe they transferred, it doesn't say. So 68 to 100. And Southeastern admits about, at least in the fall semesters, they admit about a little over 2,000 students. So I rounded it down to 2,000 students each fall semester. How many are expected to still be enrolled at Southeastern in the year? So 68 students are expected to stick around out of 100 students. 68 to 100. Southeastern admits about 2,000 students. Where'd the 2,000 go? It's going to be at the bottom. Again, this is kind of an easier problem, but I wanted to show everybody something a little bit more relevant. So we're trying to figure out the numerator here, x. How many students are going to stick around? And so we can cross multiply. I mean, ultimately, we're just finding 68% of 2,000. And this is kind of the derivation behind why We look at that in particular. So 68 times 2,000 is equal to 100 times x. So is that 100? 136. Get some zeros. 68 times 2,000. 136 with some zeros. 0. 100 times x. Of course, we divide both sides by 100. Which is pretty easy to do if you know to just trim off some zeros. So we're expected to lose a little over 400 students in each incoming class after the first year. So that's 400-ish less students you have to worry about. So that's how many are expected to stick around, roughly. So kind of interesting. Okay, let's move on to example 7, which might be probably the first kind of complicated one that we look at. So there's some tablet of medication. There's 2 substances in the ratio of 9 to 5. Oh, okay, well, they told us one for free. Ratio of 9 to 5. And they told us, okay, cool. If the tablet contains 168 milligrams of medication, how much is each substance in the tablet? Okay, so you're probably dying to put that 168 either in the numerator or the denominator. And neither one is correct. So the thing is, the 9, all right, there's 2 substances. So one of these would be substance A and substance B. The 168 is not substance A or B. It's the combined value of the 2 substances. It's the combined value. So there might be 160 milligrams of one substance and then 8 milligrams of the other. And when you add those 2 numbers together, that's 168. Or it could be a whole assortment of different mixed values that add to be 168. But how do we generalize this? That's the question here. How do we generalize that? How do we find something for substance A and substance B such that their sum gives us 168 every time? And no, we do not just make up values, or else there wouldn't be an x to solve for. Wait a minute, an x. We need an x. Make substance A just x. And the million-dollar question, what would substance B end up becoming?
I know it's probably gonna be wrong, but I was thinking maybe we do 9 divided by 5, and then you put a train back on.
You're really close. That's really close. There's a 168 minus x here. Because if substance A and substance B have to add together to give us 168, well, basically what we did is we got A by itself. And how do you get A by itself? Subtract B on both sides. Or actually, we're getting B by itself, in other words, if we want to be technical. A plus B was 168. We're subtracting A on both sides. And so that's pretty much where this is coming from. So now their sum is guaranteed to be 168, and we're not making any assumptions about what the values are. This is what makes this one probably the most difficult one in the homework, in my opinion. And so that's why I wanted to clear it up with everyone. Yes.
Or you could do 9 to 5. I have it in my head. No.
Maybe it will come up when I'm done with the problem.
Well, I'm trying to figure out if you see how 168 or something 9 to 5.
Well, ultimately, substance A, will go in the numerator. 168 minus x will go in the denominator. This is going to be a little bit more elaborate algebra here. So that's how this is being associated with the 9 to 5. Again, that's what makes this one probably the most engaged problem in the homework. So have that off to the side. We're not going to mess with that anymore. So let's go ahead and cross multiply. Cross, cross. And it's going to be 9 times. All right, I'm going to write this down. It's not going to be entirely correct. What is incorrect about what I just wrote down?
You need to have parentheses around the 168 and then minus x because you're multiplying not just 168 minus x, but also negative x.
Yeah, you're multiplying the whole denominator. That whole denominator is a single entity. 168 minus x is one number. So 9 has to multiply that whole number, not just part of that number. That wouldn't be very fair. You need to multiply the whole denominator. That's why those parentheses are very important. And then that implies that we distribute. You might remember the distributive property. If not, we're going to see it a little bit more later on. And so we can go ahead and figure that out right fast. 9 times 168, 1512. 9 times negative x is negative 9x. That's equal to 5x. So that's the result of the distribution. All right, so this seems a little bit more elaborate. Now, how do we proceed?
Alright, 15, 12. No,
Add 9x.
add 9.
Gonna add 9x on both sides. Those are called like terms. Those are called like terms. We're adding because that's the opposite of the subtracting that the 9x is doing. Cancel, cancel. So basically it's just 5 plus 9, and then we carry an x over. So 5 plus 9 is, of course, 14. And there's still an x that you better not let disappear. And now that we simplify it to this form, one more thing we have to do is divide 14 on both sides, which comes out to be this. So 1512 divided by 14, 108. The interesting thing is, though, we're not done with the problem because they want to know how many of each substance. We only figured out substance A. Because remember, substance A is X. We just found that X is 108. How do we figure out substance B? Yeah.
I was about to ask, so we said it was 168, right?
Yes. I'm guessing that's what you were about to say.
Yeah, I was going to plug it into the equation.
Yep. So 108 is for substance A. And you know that the substances have to add together to give you 168. So really substance B is 168 minus the 108 we just found, which is just 60. So really we have two answers here. The 108 for the first substance and the 60 for the second. And notice this was not making any assumption about what the values of substance A nor substance B were. We just knew that they had to abide by a ratio of 9 to 5. Does anyone have any questions about this? I promise they're all a little bit easier than this. This one's the worst one. If not, let's look at another one, which might be a little bit more helpful, especially if you're into nutrition. So there's a cereal box, nutrition information, you know, that stuff that shows up on the cereal box. And a third of a cup serving is about 140 calories and 2 grams of dietary fiber. Basically, you want to see how all of this stuff scales to, instead of 1/3 of a cup, to 1/2 of a cup. So you're trying to figure out, well, it says how many calories and grams. So these are two separate problems. We're going to start off with how many calories. So we'll do the calories one off to the side. We'll do calories, we'll do that one first. Grams we'll do over here of fiber. Do that one over there. So we'll get to that one later. Start off with calories. So with the calories, what's a ratio that we have? Yeah, so we have 1/3 over 140. A third of a cup, 140 calories. All right, that's a ratio. So what would be the other ratio?
Half a cup over X.
Yeah, so some students in the past have been tempted to do something with that 2. That 2 is for the grams of fiber. We're not touching that yet. We want to figure out what happens with a 1/2 cup serving. So the 1/2 cup's going to go in the numerator because that's where the cups go. That's where the cups go. So that means the denominator is, well, we don't know. That's the calorie one. Notice how the measurements, the units, labels, whatever, they have to stay aligned. Cups are in the numerator, calories are in the denominator. You have that, that is a necessary part of proportions. But from here, we can cross multiply. It's just kind of a nuisance that we have a bunch of fractions within fractions. So let's try to clean this up. So that's 1/3 times x is equal to 140 times 1/2. Well, the good news is we can take care of one of these fractions. So x is equal to, well, 140. What's 1/2 of 140? Is 7. And then x is really close to being dealt with. Just have to do one more thing. And just multiply 3 on both sides. There's that pesky 3 in the denominator. We need to get rid of that. Pesky 3 goes away. X is 70 times 3, 210. So that's the calories. So that's one part. But then it moves over to the other side and says, well, what about grams of fiber? So now what ratio do we start off with?
1/3
1/3 and what?
over 2.
Over 2, that's right. Because they go on to say 2 grams of fiber. And that's corresponding to 1/3 of a cup. Pretty straightforward stuff. 2 grams of fiber. I'll just put 2 fiber. And we know that this needs to correspond or translate to a 1/2 cup. So it's virtually the same problem, except there's a 2 there instead of 140. And some slightly different labels for fiber instead of calories. Let's go ahead and cross multiply. 1/3 times x is equal to 2 times 1/2, which we can clean that up pretty quickly. 2 times 1/2 is just 1. And it's really the same problem we had before. Multiply by 3 to get rid of that pesky 3 in the denominator. It's cancel. X is simply 3. Okay, does anyone have any questions before we move on? If not, we're going to move on to some basic algebra. So there's the last part of the section just deals with basic algebra. Again, if you're comfortable with algebra, you might be able to knock this section out really quickly. Just a few ideas corresponding to linear equations, such as like terms, distribution, and the least common denominator. So that's pretty much to the extent for which this goes. And so we'll start off with really problem 1 here. So problem 1, they try to trip us up by putting m's instead of x's. So I don't know, does that obstruct people in any way? Are the m's intimidating, or do you know what to do?
You do it the same way.
And what would be the first step in that process? And what would be that process?
Either subtract 2 on both sides or add 6. So subtract.
Yeah, good catch. So you need to get the like terms together. You need to get those like terms together. And again, everything that's a like terms are numbers that have the same variable, or maybe not have a variable. Those would also be like terms. So there's the 2m and the 6m. They both have m's, so they're like terms. You need to get them together. So you can either move the 2 over or the 6 over. But anytime you move something over, you have to do the opposite operation. So here, the 2m is being added to the 25, so we need to subtract 2m. And the reason why I'm choosing 2m is because the difference on the other side is going to stay positive. It's normally a good intuition. You could subtract the 6m on both sides, but then you'd have a negative number. And some people don't like those too much. So cancel, cancel. We'll just leave it at that for now. So now that's 25 is equal to 6m minus 2m. Just 6 minus 2 with an m. It's 4m. And there's a minus 3 over there, because that doesn't disappear. It's just kind of there. But we still have more like terms, because the 25 and the 3 can be combined. And again, I'm going to add the 3 on both sides. I'm adding, of course, because we're subtracting. You have to do the opposite. And I'm moving the 3 over to the 25. Mainly, the intuition is you want to keep positive numbers if you can. So they're a little bit easier to work with. So that's 28 is equal to 4m. And then this form looks familiar. We're multiplying 4 times m. The 4 is kind of getting in the way, so we divide both sides by 4. M is 28 divided by 4, which is 7. So again, if this stuff is familiar from high school, you can probably knock out this section really quickly, and the corresponding quiz. Well, problem 2, okay, they put parentheses, and they have y's instead of m's. We already established the symbols don't really matter. A symbol's a symbol. But these parentheses, does that affect our process?
Use some new distribution.
So the parentheses, keep in mind, the parentheses are kind of emphasizing an important process that we have to do. We cannot combine like terms yet because we don't have all the terms separated term by term. Basically, these parentheses are telling us we need to do a little bit more work before we can start combining like terms. And as we did before, this is distribution. You have a number that's in front, or multiplying a parenthesis, you have to distribute the front number to all the middle terms. Basically, every term inside the parentheses needs to get a piece of the multiplication on the outside. So just to write this out a little bit more deliberately, that's 5 times 3y minus 5 times 1. Just to write out those first few steps. And then we just have 3 times 2y. I guess it's technically distribution. I mean, you're really just distributing to one term, so it's really just multiplication. So that would be negative 6y, because negative 3 times 2 is negative 6, and there's a y there, and that's 19. So that would be the first step as laid out as possible. 5 times 3 is 15, minus 5 times 1 is 5, minus 6y is equal to 19. And I want to ask this now and see if anyone gives a certain answer. What do we do next? Say that again?
Combine 15y and negative 6y.
Yes, so a lot of people will say add the 6y to the 15y because you're so used to moving things to the other side of the equation, but you might not notice they're already right next to each other on the same side of the equation. So you don't have to do the opposite operation. They're already right next to each other. So you could just subtract them in this case directly. You don't have to move them across the equal sign, so you don't have to do the opposite. 15y minus 6y, well, it's just 15 minus 6, that's 9y. And there's a minus 5 that just kind of hangs around. Of course, it's equal to 19. And then, well, we have more like terms, those numbers you can get together. So add 5, 9y is equal to 24. And then we can just divide the 9 on both sides. 24 divided by 9. Knowing my math lab, they'll probably ask for a simplified fraction. (24) divided by 9. And let's convert that to a fraction. 8 over 3. That is our final answer. Does anyone have any questions about this one? Okay, well, let's move on to the, I'm glad I wasn't the only one who heard that. Let's move on to problem 3. 5x plus 22, and they put some parentheses, x minus 4 is equal to 236. Well, as we saw in the previous problem, there's a number multiplying some parentheses, so we need to address that first. Go ahead and distribute like we did before. So this will be 5x plus, and just to write it out in case anyone might not remember distribution, that'd be 22 times the first number in the parentheses, x, minus 22 times the 4, equal to 236. And we can clean that up fast. 22x, and that's going to be 22, 44, 66, 88, equal to 236. And now everything's term by term, which means we can just add like terms. Well, the 5 and the 22 are right next to each other, 27. Well, we have more like terms. The 88 well, the negative 88 and the positive 236. You can get them together. X is equal to 236 plus 88. 236 plus 8, 324. And of course, we divide both sides by 27, and we're done. Simple as that. 324 divided by 27. That's 12. So how's everyone feel about those so far? Pretty straightforward? Okay, well, problem 4 is a fraction. And for some people, well, a lot of people don't like fractions at all. I very much hate them, actually. So normally my philosophy is if I see fractions, I'm going to get rid of fractions first, no matter what. But that means you need to know how to get rid of the fractions. And normally I use the least common denominator, which is the least common multiple of all the denominators. So if you can figure out the smallest number that all the denominators can multiply into, or even you can find a common denominator by just multiplying all the denominators together, if you just didn't care about the messiness of the number. But if you can find the smallest number that all of your denominators go into, which means divide into, then that would be your least common denominator. Now for problem 4, that's going to be a very easy task because we only have one denominator, 7. What's the smallest number that 7 can go into? 7. Yeah, not very exciting. 7 goes into itself. So the least common denominator would be 7. And so what do you do with a least common denominator? You multiply to every single term in your problem. That term is always separated by an addition or subtraction sign. That will include, so every term, in fact, let me rewrite it just to emphasize it, make it a little bit larger. 7 minus 3 equal to x over 7. And you multiply every single term by a 7, even the 3. The 3 doesn't even have a denominator, but it doesn't matter. Every term. This is how you balance the equation. Basically scaling the equation by 7. And this is a convenience for us. So for the first fraction, really, those 7s cancel. That was convenient. And this is the goal of the least common denominator. We should not have any fractions after we do this. That's why we're doing this. That's x. Well, then it's 3 times 7 for the next one. That's 21. And then these 7s, well, they cancel again. That's just x. What do we do next? Yeah, which x should I move where? I guess really it doesn't matter. Let's subtract that x over here. Get the negative 21 by itself. But look what happens. X minus x is 0. X minus x is 0. It's odd. So we're getting negative 21 is equal to 0? Did we do something wrong here? I mean, we didn't do anything wrong. We just found an equation that yields no solutions. So really, what we did was fine. But of course, negative 21 doesn't equal 0. That's ludicrous. So no solutions is the answer.
Isn't no solutions different than undefined? Like with undefined, when you like x equals 0, and that's undefined,
X.
versus like 21, negative 21.
So undefined, asking that to a mathematician might define it in a different way. I feel as though undefined, I'm trying to think of situations. Are you talking about a college algebra class that you've taken where you had
I
a,
just like remember, I took like, I think it's like pre-calculus or something like that, and then it was like, you had to graph them, and there were like different ways to, like,
So
I
you're-
think I remember like graphing undefined ones, but not, I just couldn't remember.
well, undefined, what, the first thing that comes to mind is whenever you have rational functions, so rational just meaning fraction, and you find a value at the very end, but that value doesn't work when you plug it back into the original equation, and that would be an undefined value. That's the only thing I can think of offhand. Besides for that, when I think of undefined, I mean, I think personally that undefined means you can't even continue. You wouldn't even be able to work out this problem to get no solution as an answer. But asking a mathematician might be a little bit different than asking somebody else. Like in the calculator, if you go in the calculator and type in 1 divided by 0, you're going to get an error, an undefined error. It's because you can't even get an answer in the first place. Here we got an answer. It just didn't equate to any solutions. But then the other one was just a straight up error, which meant we couldn't even make a conclusion based off of it. Kind of a philosophical thing, but leave it to a math person to overthink something. But hopefully that kind of answers your question. You won't have to worry about undefined stuff in this class, though. At least, yeah, in this class, it doesn't come up. So, fun philosophical rant aside, let's look at problem 5. Okay. Problem 5. All right, now we have some different denominators. So this is great. Now I see, so my thought process, I see fractions, I get rid of fractions, which immediately makes me think, all right, let's figure out the LCD. The LCD is the smallest number that every denominator will go into, the 9, the 3, and the 18. What is the smallest number that a 9, a 3, and an 18 will go into? What's that? So I think I remember from last semester when I taught this, a lot of people said 9, which of course 9 goes into 9, and 3 goes into 9, but I think they might think about it the wrong way. 18 does not go into 9. Or in other words, so if you were to say it was 9, then you would imply that 9 divided by 18 is a whole number, which it's not. You're picking this number on purpose because whenever you do this multiplication, you want your denominators to cancel out. Or at least the denominator, yeah, you want the denominators to cancel out. So the least common denominator here is 18. 9 goes into 18 2 times. 3 goes into 18 6 times. 18 goes into itself 1 time. So let's put that to the test. You can find out pretty quickly if you chose the right LCD or not based off of how the fractions go together. I'll give this a little bit of space so I can throw in the 18. So multiply times 18 times 18 times 18. You multiply every term by the least common denominator that you found. Now for the first one, well, in general, LCDs are used to look at what does that combination yield. There's a 9 in the denominator and an 18 as your least common denominator. 18 divided by 9 is 2. So it doesn't cancel out. It's just that the fraction of 18 divided by 9, well, it gives you a whole number. No more fractions. Have a question?
Why are we not multiplying 18?
Why are you not multiplying 18?
By 9 and 18 times 3.
So you're asking why are we not multiplying 18 to 9?
Yeah, because remember how if you have the denominator, you want to multiply by both sides to decide the fraction.
Well, what we're doing here is we're technically distributing at 18. So we're multiplying the 18 on the left, but we're distributing, which means the 18 is being multiplied to the x divided by 9 as one number, and to the 1/3 as one number. And so, and the 9's stuck in the denominator, the 18 is in the numerator. So we really are multiplying by both sides, but we're really skipping the step of distribution. But that is where it's coming from. And so what we have left over is an x and a 2. And everything's being multiplied here. That would be 2x. So let's try that again with the next one. With LCD, we generally look at this diagonal here. The denominator we want to get rid of versus the least common denominator we have now implemented. 18 divided by 3, 6. So of course, there's a plus sign there. And what are we left with? A 1 technically, and a 6. 1 times 6, which is just 6. And then this is equal to, all right, we have 1/18 times 18. 18 divided by itself is 1. 1 times 1 is 1. A lot of people want to put 0 in this situation because they'll see that the 18's cancel and think, all right, well then we have 0. 18 divided by itself is 1, not 0. So this is what we have left over. But once you clear out the fractions, notice how easy the problem gets. I mean, it's a very simple problem from here. Subtract 6 on both sides. So we get -5, and then we divide 2 on both sides. We get -5/2. Because that fraction doesn't really simplify anymore. Does anyone have any questions about the implementation of the least common denominator? I mean, if not, problem 6, we're also going to look at one. I mean, it was this stuff, so true story. So it was this stuff that made me fail algebra in high school. I was not good at math in high school. I failed it big time. I know, kind of weird, but I couldn't understand like terms to save my life. So you probably all have a better basis than I did for high school math, or this kind of math. So let's look at problem 6 as well. So I see fraction. I want to get rid of fraction. Makes me think, let's use the least common denominator. All the denominators we have a 5 and a 6. What's the smallest number that 5 and 6 both go into?
30.
It's 30. Okay, cool. Rule of thumb, you can multiply them together. 5 times 6 is 30. And you'll get at least a common denominator, which will work. Doesn't have to be the least one. So I'm going to write out everything again, just so I can illustrate the multiplication. Equals 7/6. So let's multiply each one of these by 30. Now, each one of these situations, looking at how the denominator compares with the least common denominator. 30 divided by 5, that's 6. We have an x left over and a 6 left over. So that'd just be 6 times x. All right, let's do the next one. There's a minus sign. 30 and 6. Well, 6 goes into 30 5 times. An x left over and a 5 left over. So 5x. Next one. 6 goes into 30, again, 5 times. We have a 7 left over, a 5 left over. And remember, this is all multiplication, so don't add these two together. This is multiplication. 7 times 5 is 35. Did I lose anybody so far?
Wait, repeat the last one?
Which five? Oh, the last one?
Yeah.
It's just, how many times does 6 go into 30?
And then why you didn't do 7 times 30? Then you do 7 times 5.
Well, I mean, you could have done 7 times 30, but then you still have the 6 in the denominator. I'm just trying to get rid of the fraction as quickly as possible. And so the way you do that is you always compare the fractions to the least common denominator, regardless of what the numerator is. Notice I ignore the numerator first, and then I bring it in at the end. So for the very first one, I looked at 30 divided by 5, which gave us 6. And then I compared the 6, and then I brought the 6 and the x together. Notice that x in the numerator just kind of stayed there, just hung out off to the side until I was done getting rid of the denominator. But then from here, it clears up rather nicely. And then we have 6x minus 5x. It's basically just asking to be, simplified. 6x minus 5x is simply x. And really, it just solves itself because we don't have to get x by itself. It kind of just happened naturally. So x is 35. So are there any questions up to this point? Because if not, I guess I'll reiterate the workbook assignment, which I believe is workbook 5. I think we're on number 5. So workbook number 5 is going to be 3 pages. 2 of those pages will be from the section. Page 15, numbers 3 and 4. Page 16, number 2 and 3. And then eventually, when we get to the statistics section, page 17, numbers 1 and 2. And that'll be due Friday. Besides for that, the homework for this section is due Wednesday, and the quiz is due Thursday. And the workbook's Friday. Other than that, that's all I have. Have a good day. Sign the roll sheet if you didn't do so already, by the way.